Hello guys, do you want to get tips and tricks to remember carbohydrates forever? Then watch this video till end. My dear viewers, Assalamu alaikum wa rahmatullahi wa barakatuhu. I welcome you again to my channel AmreenaMehrajTutorials. If you haven't subscribed my channel yet, do subscribe. Let's get started. So continuing our topic, we're going to continue carbohydrates. And our topic for today is going to be very important. It's isomerism in monosaccharides. This is very important. And it will be helpful for chemistry also. And you will get a bit of physics also over here. So what is basically isomerism and what are isomers? This is not unknown to you people. You know isomerism phenomenon from class 10th maybe. Because you have this chapter called carbon and compounds in your foundation classes, where you study about different types of isomerisms which are possible in hydrocarbons. So this is nothing different from that. So to give you an idea what isomerism is, I will take some examples here. I'll be quoting this example. Let you check yourself whether you have learned something out of my previous lectures or not. So this is C double bond OH. Then this is C H OH C OH H C H OH C H OH C H2OH. 1, 2, 3, 4, 5, 6 carbon polyhydroxy with an aldehyde group. This is a carbohydrate. Can you name it? This is what? This is glucose. Very good. Can you tell me its molecular formula? This is C6H12O6. Okay. I'll be drawing another molecule in the side. It's like this. CH2OH C double bond O C H OH C H OH C H OH. I have 1, 2, 3, 4, 5 done. Then CH2OH. Can you label what is it? It's polyhydroxy, ketone, carbohydrate under ketose. This is actually fructose. Very good. And what is its molecular formula? C6H12O6. My dear students, observe. Molecular formula is same, isn't it? So, they have same molecular formula. What do they differ in? How do they differ from each other? They differ in what? They differ in terms of arrangement of atoms. They differ in terms of their structure. So what is different between them? So difference is what? Difference lies in what? Structural formula. Okay? Any such compounds which have same molecular formula, C6H12O6, C6H12O6. It's just a basic example. So any molecules which have same molecular formula, but they have got different structures, they have got different structural formulae, they are called isomers. So what are they basically? They belong to each other as being isomers. So we can call glucose and fructose are isomers of each other. Now there are different categories of isomerism. Isomers could be of different categories. You have to understand about them. So isomers are what? For molecules which have got same molecular formula, but they have got different structural formula. They are called what? Isomers, and this phenomenon is called iso. Now see the isomers which are possible in monosaccharides. You will see 4 types of isomers here. Whatever we are going to study right now is going to help you in chemistry also. 4 types of isomers. Number 1 type is going to be D and L isomers. Usually students have a kind of phobia to these things, but I will make it very easy, I promise you that. D and L isomers, they are also called enantiomers. Okay? second type of isomers which I'll be discussing with you is going to take you to the world of physics, which I love a lot. Second is optical isomers. You'll get something to know about light in this. And third is about ANOMERS. Okay, I'll be teaching you them also. And the last category which we'll discuss inshallah is going to be EPIMERS. They are somewhere, related to each other. They are not absolutely different. They are related to each other. But in order to memorize them for NEET and AIIMS and other examinations, you need to flow like this, okay? You have to put everything in a systematic manner so that you will be able to memorize it for longer terms. That's why I said you will get tips and tricks today. Let me begin with what D and L isomers, which are also called enantiomers. This lecture is going to be, giving you benefit in chemistry also. A lot of benefit, because usually students have a lot of problem with, organic part of chemistry and isomerisms and all. So this will help you, inshallah. As far as D and L isomers are concerned, I will not give you definition. I will not give you that rote learning concept. Let us straight away go to an example. I'll be drawing open form, which you call Fischer projection. I'll be drawing one Fischer projection. Have a keen observation on that Fischer projection and try to observe what I am drawing, okay? So this is C double bond O H. Observe, I have placed double bond O from left side. Otherwise, I used to place it in any direction. Now I have to be very specific as far as orientation of atoms is concerned. Then I will simplify things. I will draw a straight line. Then I will draw 4 horizontal lines. 1, 2, 3, 4. This will save our time. And each intersection point, look at this intersection point, this intersection point, this intersection point, this intersection point. They represent carbon atoms, okay? Now I will be showing like this. I'll go like this, H, OH, OH, H, H, OH, H, OH, and then you have what? CH2OH. This is glucose, okay? That is known to us. Now let us see what type of glucose it is, whether it is D glucose or L glucose. For that matter, to understand what enantiomerism is, you have to first of all get this idea about chiral carbon. I hope you might be knowing, many of you might be knowing, but those who have confusion, let me make it very simple. A carbon atom which is attached to 4 different groups, okay? If you take a carbon atom and this carbon atom is attached to 4 different groups, then you call that carbon chiral carbon. What do you call it? Chiral. What is the valency of carbon? It can form how many bonds maximum? 1, 2, 3, 4. Okay. If your carbon is attached to 4 different groups, like from this it's X group, here it's Y group, here it's Z group, here it's A group. So you have how many different groups attached to carbon? 4 different groups. Then you'll call this carbon, which carbon? Chiral carbon. This is called, this carbon then becomes a chiral center. Okay. Or you can call it a stereo center. Okay. Then it has got some specific properties as far as symmetry is concerned. If it's not attached to different, groups, then it becomes achiral. Okay. So here, in case of this enantiomerism, you have to find out, first of all, what? You have to find out chiral carbons. Now let us find out chiral carbons. Is this carbon chiral carbon? This is carbon number 1. This is carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. Is this chiral carbon? No. It's attached to 3 groups only. It's not having 4 groups also. It's attached to oxygen, hydrogen, and this long chain. So this doesn't satisfy the condition for chirality. Okay, leave it. Go to carbon number 2. Is it a chiral carbon? Yes. See, on one side it is attached to aldehyde group. On another side it's attached to OH group. On another side it's attached to hydrogen. And from this side it's attached to a long group which is made up of how many carbons? 1, 2, 3, 4. So isn't this carbon chiral carbon? Yes. So carbon number 2 is chiral. Agree? Look at carbon number 3. This is attached to this chain of 2 carbon atoms. Then it's attached to H, another group. It's attached to OH, another group. It's attached to a chain of 3 carbons. 1, 2, 3. So on one side you have a chain. If you look at this, I will place my pen at this carbon. On one side you have chain of 2 carbons. On another side you have chain of 3 carbons. On another side you have OH. On another side you have H. Is this chiral? Yes, because it's attached to 4 different groups. So carbon number 3 is also chiral. Okay. Now look at carbon number 4. Is it chiral? On one side you have a chain of 3 carbons. On another side you have a chain of, I have to keep it always correct, okay? From one side you have a chain of 2 carbons. From another side you have a chain of 3 carbons. From this side you have hydrogen. From this side you have hydroxyl. This is also attached to 4 different groups. So carbon number 4 is also chiral. Look at carbon number 5. I will place my pen now carefully. So on this side you have a chain of 1, 2, 3, 4 carbons. Here you have CH2OH on other side. Here you have H. Here you have OH. 4 different groups. That means carbon number 5 is also chiral. Okay. And as far as carbon number 6 is concerned, look at this carbon number 6. It has H2. That means it's attached to H. H. Then on the top there is a long chain. Long chain of what? 1, 2, 3, 4, 5 carbons. That is there. And on other side it's attached to OH. See, it's attached to OH. 2 groups are different. Same. H is same. That means this is not a chiral carbon because it has 2 H's. Both H's are what? They are similar. So you need to have 4 different groups. That means this carbon, carbon number 6, is not a chiral carbon. Okay. So how many chiral centers you got in this glucose? 1, 2, 3, 4 chiral carbons. Now this was the first step. You have to find out chiral carbons. So you found them. Now out of them you have to select the farthest chiral carbon. Farthest chiral carbon. Now your question will be, ma'am, from which side we will look whether it's farther or not. Do we have to go like farther from base or farther from top? No. You have to always move farther from the, you have to go furthest from the functional group. So which is your functional group here? It's aldehyde group. So look at the functional group. Which is the chiral carbon which is farthest from the functional group? Is it 2, 3, 4 or 5? This is 2 farther from functional group? No. Is 3 farther? No. Is 4 farther? It is, but which is the farthest? 5. Okay. So we will select which carbon? Carbon number 5. So out of them we have selected which carbon? Carbon number 5. Okay. Now your point of attraction is what? Carbon number 5. Look at this carbon number 5 and observe which group? OH group. What is the direction of OH group? Is it towards right or left? OH group is towards right. If the OH group is towards right, then you call it D-glucose. Okay. So if OH group is towards right side, what do you call this sugar? D-isomer. If the same OH group will be towards what? If it will be towards left side, then you will call it L sugar. Let us practice again. So, how do you come to know what enantiomerism is? Any two compounds which differ in what? Orientation of hydroxyl group. On which carbon? On chiral carbon. But which chiral carbon? That chiral carbon which is farthest from the functional group. If that OH group is towards right, you will call it a D-isomer. If the same OH group is towards left, you will call it an L-isomer. Now, how do you reach to this point? What is the strategy to get this D-isomer? First of all, you have to find chiral carbon, a carbon which is attached to 4 different groups. How you will find? You have to observe keenly and you have to see how many chiral centers you have. Then you have to count them. We have done a drill. We studied carbon number 1, we found that it's not chiral. Then carbon number 2, 3, 4, 5, they were chiral. Then we have to select that chiral carbon which is very far from the functional group. So I have written that chiral carbon which is farthest from what? Functional group. That was which in this case? Carbon number 5. And then around this farthest chiral carbon, you have to look at the position of hydroxyl group. If hydroxyl group near this chiral carbon is towards right, it will be your D sugar. So this one is our D glucose. Now let us try and draw its what? L isomer. What will be that? In that you will have to place this in opposite direction. Simply you have to get the mirror image. Mirror image of what? Mirror image of this D glucose will be the L glucose. So these points will help you to understand what enantiomers are. So let me rub this off and let me now draw L glucose with you people. So L glucose, for that, what are you supposed to do? Your actually point of attraction is OH, but L glucose hasn't only OH towards left. All the groups are now going to be placed in an opposite direction. That means you have to get what? You have to draw a mirror image. So here, see, double bond O was towards left. Now it will be towards right. H will go towards left. Same. 1, 2, 3, 4. CH2 OH. Now HOH will be mirror now. OH H. This was OH now H OH. This was HOH OH H. This was HOH OH H. Same thing. Where is now the position of your OH group at carbon number 5? It's towards left. This is going to be the L isomer, or what you call L glucose. So what are D isomers? D isomers are those isomers in which what? OH group is towards right. But is it any OH group? No. OH group is towards right in case of chiral carbon, which is farthest from functional group. And in case of L sugar, what do you have? OH is towards what? Left. In case of which carbon? In case of chiral carbon. Which is the chiral carbon you are considering in this case? It's carbon number 5, which is farthest from functional group. That defines your enantiomers also. So enantiomers are those isomers which differ in what? Arrangement of hydroxyl group around the chiral carbon, which is farthest from the functional group. So this is the way in which you come to understand the concept of enantiomerism, and you got to understand what D isomer is and what L isomer is. So now you know about D glucose and L glucose. I have already taught you about that these open chains in aqueous medium, you will find them in what? Closed rings. And in case of glucose, you will find 5-membered rings as well as 6-membered rings. Now I will be next showing you, we will convert this Fischer open chain form into a closed ring. and I will show you how can we designate whether a closed ring form of glucose is D form or L form. That is also very. Let's now convert this Fischer projection, open form, into Haworth projection, that is closed form. I have taught you about that in my previous videos. And to get that closed conformation, you have to react this aldehyde carbon with this hydroxyl group so that a closed ring is formed. In order to see whether a closed form is D sugar or L sugar, your point of attraction changes. Now in that case, in closed ring form, your point of attraction will be this group, CH2OH group. I'm talking about which form? Closed form. So let us first of all draw the closed form or Haworth projection of which glucose? D glucose. So it will be like this. O, I'll be going with the hexagonal ring. I'll be going with this hexagonal ring for glucose. So over here, this represents your carbon number 1. This corner represents carbon number 2. This corner represents carbon number 3. This corner represents carbon number 4. This carbon represents carbon number 5. Then to the carbon number 1, once you have this converted into ring, groups will be like this. You will have H, OH. Then carbon number 2 will have H, OH. Then carbon number 3, you will have OH, H. Over here, you will have H, OH. And over here, now look at this, CH2OH. If you will place this CH2OH group on the top, okay, here I will place it on top. And H I will place in bottom. Okay, so you have carbon number 5 to this. What is attached? Carbon number 6. That means what is attached to carbon number 5? C6, CH2OH. So this is carbon number 5. From one side, what is attached to it? CH2OH. And from other side, what is attached to it? H. So this is the carbon in the ring. From one side, you have CH2OH to it. And from other side, you have H to it. Okay. This has become the part of the ring. Okay. Now, I have placed this group. Which group? CH2OH group. I have placed this group towards the top of the plane. If it's towards top, then this is which glucose? D glucose. So that's why I said your point of attraction will now change. When you have which form? Ring form. At that time, you don't have to look at what? You don't have to look at chiral centers and all. You have to look at what? CH2OH. If it's towards the top position, it's D glucose. If you will shift now this group towards the bottom and you will get this H towards the top, then it will become which? L glucose. This is carbon number 1, 2, I mean to say this. Carbon number 1, 2, 3, 4, 5. H, OH, H, OH, OH, H, H, OH. Now, if I will shift this CH2OH, if I will shift this to downward direction, so now it will not remain on top, it will come to bottom. So it's like this, H will go up and you will have over here CH2OH. Then what I have done? CH2OH towards bottom. So you have this towards lower position. This is your L glucose. So you have D and L isomers in open forms as well as in closed forms. In open forms, you analyzed farthest chiral carbon and you saw OH. If it's towards right, it's D. If it's towards left, it's L. If you convert them into rings, then you have to look at which group? CH2OH. If the CH2OH is towards top, it's D glucose. If it's towards bottom, This is L-glucose. So this board right now is having information about open forms. Now understand the second type of isomerism. I'll be now taking ANOMERS. Why I'm taking ANOMERS? Because ANOMERS are possible in case of closed ring forms. Right now I taught you about what? Ring forms. When I saw D-glucose and L-glucose. So with the same concept, it will be very easy for you to remember this. I have kept D-glucose over here. Why is it called D-glucose? Because CH2OH is on the top. Now let us learn about its anomers. Once we will learn its anomers, you will remember them permanently and you will have this concept of anomerism forever done. See, in case of anomers, you have to look at what? You have to look at this carbon. In case of glucose, this carbon is called anomeric carbon. What is it called? Anomeric carbon. If you remember the open form of this glucose, I'll be quickly showing you. Okay, this is like this. Over here you have CH2OH. Till now you are familiar with this thing, so I can rush through it. OH, H, H, OH, H, OH. This is clear to you. Earlier you had a structure like this, and in this case there was different concept of labeling it as D or L. Now my point over here is to make you understand about what? I want to make you understand about anomeric carbon. What is it? Okay. This is which carbon? Carbon number 1. What is its actual position? This is actually which carbon? This carbon. So earlier it was an aldehyde carbon. Now it's not an aldehyde carbon. This has now become a hemiacetal, which we have discussed earlier. It was here achiral. What was it? Achiral carbon, because it was not attached to 4 different groups. Now once a ring was formed, once this aldehyde group, once this carbon reacted with what? This hydroxyl group, it resulted in the formation of ring. And in the ring, if you observe this carbon, it becomes chiral. It's now attached to 4 different groups. It's attached to H, OH, O and C. So now it has attained chirality. We call this carbon now anomeric carbon. So anomeric carbon is the chiral carbon, or you can say it's the hemiacetal carbon, to remember. Okay, now it's the hemiacetal carbon which has become chiral. You have to observe this anomeric carbon to understand about anomers. So this is your point of attraction now. You got this idea what anomeric carbon is? It's the carbon number 1 in case of glucose, which was earlier aldehyde carbon. Now it's the carbon number 1 in case of ring, which has become what? It has now become a chiral carbon, which is attached to 4 different groups. And let us now see what anomers are. And what are the anomers of D-glucose? If I make this again, let me show you here. So in this case, what you have? In this case, HOH. And over here, you have CH2OH and H. Why I have drawn only this portion out of this? Because we have to focus only on this portion. Rather, we have to focus only on these 2 groups, which I will highlight. This group and this group. We have to focus only these 2 groups. Okay? Rest we are not concerned with. So we are concerned with anomeric carbon, and we have to look at the OH group, which is attached to anomeric carbon, and we have to look at this CH2OH group. Okay? Which is attached to carbon number 5. So this is carbon number 1, carbon number 5. They are our point of attraction in this case. That's why I have retained this diagram, so that you will come to understand that they are related. Okay? What is this technically? As per D and L form, is it D or L? This is D-glucose. That is done. But if you look at this OH, what is its direction? Is it opposite to CH2OH or is it in the same direction as CH2OH is? It is opposite. If the OH group, so I'll write down for you. If the OH group on which carbon? Anomeric carbon is in opposite plane of what? Of CH2OH group. Then in this condition, my dear students, in this condition, it becomes alpha D-glucose. So you have one form which is called which form? Alpha form. So anomers are of two types. Alpha form. Can you guess about the opposite? Opposite is like this. See, it's very easy, but tricky. Same, everything is same. CH2OH is in the same direction. But what happens to OH? It was earlier downward. Now it will shift to upward direction. Rest is all same as this. Okay. So what is this? Ma'am, it's of course D-glucose. Okay. Because CH2OH is on top. CH2OH is on top. It's what? D-glucose. So this is D, this is D. But what has happened to what? What has happened to OH? It has shifted to upward direction. Or it is no more opposite. It is no more opposite to the plane of CH2OH. It's not opposite to CH2OH. It is in the plane of CH2OH. It is beta D-glucose. Okay. So what is alpha D-glucose? And what is beta D-glucose? Rather, what is alpha form? What is beta form? Alpha and beta are the two anomers or isomers, in which what is important is the position of OH group. Near which carbon? Anomeric carbon. If it is in opposite plane of CH2OH, then it is alpha. If OH and CH2OH are in same plane, then it's a beta D-glucose. So you came to know about anomers. What are they basically? They are a kind of isomers of a particular sugar which differ from each other only in terms of the orientation of OH group. OH group is towards the bottom, then it's alpha D-glucose. If this OH group is towards the top, then it's beta D-glucose. Or you can say like, if the OH group is in opposite plane, opposite to the plane of CH2OH, it's alpha. If this OH and CH2OH group are in the same plane, then it's beta D-glucose. Let us understand the most interesting kind of isomerism, that is third one, which is optical isomerism. This is very, very interesting, and in this case, as you can see this word, optic, it is pertaining to what? It is pertaining to light. Means you have to here understand what your monosaccharide is doing with light. Whether it is capable of rotating light or not. Okay? So you have to see this. So whether your monosaccharide is capable of rotating light or not. Accordingly, you can say your monosaccharide is optically active. When will you use this term optically active? If your monosaccharide, your sugar, is capable of what? If it rotates light. So if your monosaccharide, that is the sugar, is capable of rotating light, I will show you what this rotation means. If it is rotating light, if it can rotate light, then you will say that this isomer or this sugar or this monosaccharide is optically active. And then if it cannot rotate light, then you will say it is optically, what is the word you can use? You will see it's optically inactive. So what is the condition for saccharide to be optically inactive? It will not be able to rotate light. So if it cannot rotate light, then we will say that the sugar or isomer is optically inactive. This is very basic, okay? Now let us try and understand what this optical rotation or optical activity means and how do we come to know whether our monosaccharide will rotate light or it will not rotate light. What is that instrument in which this type of activity is measured, okay? And then what will those substances be called? Okay, let me take you to this beautiful world of physics which I love very lot. So if I am showing this on the board like this, I am showing some arrows like this. These are certain arrows I have made. What do you get to know from these arrows? You get to know that there is something which is traveling in different directions. Okay, this is actually your light, which is not traveling in just one direction. It is traveling in multiple planes. It's traveling in different planes. Now, if you will convert this light into what? If you will convert it into something like this, then you can call this light, it travels in just one plane. Here this light was traveling in multiple planes. Here it is traveling in one plane. You will call this light plane polarized light. What do you call it? Plane polarized light. And this form of light is called unpolarized light. So if you will generate light from some bulb, it will be unpolarized initially. Then what are you supposed to do? You are supposed to convert it into plane polarized light. How will you do this? You will let this light to pass through a material. This material is the polarizer. What is it? This is the polarizer. The best example of a polarizer is a Nicol prism. Okay? You can use this prism to get what? Plane polarized light. Okay? Then what do? You let this light fall on a test tube. So here I will be taking a test tube. Okay? This test tube contains a solution of monosaccharides. So what is this test tube containing? It's containing a solution of monosaccharides. A solution of monosaccharides. So you have to now see whether this solution of monosaccharides, whether the sugar present in them are optically active or they are optically inactive. Now what you will do? You will let this light fall on this test tube. Okay? Once the light will fall on the test tube, there are two chances. What are the two chances? What will happen to the light? Suppose this was the original plane of light. Okay? This was original direction plane of light. Now after falling on the solution, two possibilities are there. Either this light, which was traveling like this, either it will bend towards the right direction, or you can say it will rotate towards right direction. See, I have shown now here. Light has what? It has rotated. It was earlier like this. Now it has undergone rotation like this. Now it's traveling in which plane? In this plane. So what does this give you an indication about? Rotation of light towards right. In mathematics, you usually represent right by plus. See, if this is a number line, over here you have 0. All the numbers which fall on right side are represented by plus. The numbers which fall on left side are represented by minus. Can't we show this as this direction then? Plus Very good. In quadrant, like in coordinate geometry, we all often represent 4 quadrants. If we talk about 2-dimensional geometry, then this quadrant, it represents plus and this represents minus in terms of x-axis I am talking about. So here, since light is bending in right, so I'll use this plus. If it will bend towards left, then I will use minus. So, what is the other possibility? Right now I showed you bending or rotation towards right. Similarly, what can happen? This light, which is shown like this, it could now be possible that it may either bend towards left. So what is this representing? From here, it has now bent towards left. When? When it has passed through this solution of monosaccharides. It will either, what is this it I am using for? I am using it for plane polarized light. So plane polarized light is either bending towards right or it can bend towards left. So this represents what? This represents rotation of light towards left. So you have two things. Either right side rotation of light, either left side rotation of light. And it's not normal light. It's plane polarized light. Then you will represent this by minus. Okay. If your sugar is behaving like this, okay, then it's called dextro-rotatory sugar. What is it called? Dextro-rotatory sugar. Dextro is derived from Latin word which actually means right bending. Right. And if your sugar is behaving like this, it is rotating plane polarized light towards left, then you will call it a levorotatory sugar. Very good. So here is it, levorotatory sugar. So your monosaccharide could be either dextrarotatory or it could be levorotatory, or we can say that it could be a plus sugar, okay, or we can say it's a minus sugar, okay. Plus, because it is responsible of rotating the light towards right. Minus, because it is responsible of rotating the light towards left. Even in certain references you will find like this. They say this is which direction of rotation? Is it clockwise or anti-clockwise? So we say this is clockwise rotation. And the other one, opposite one is counter-clockwise rotation. So you want to learn that monosaccharides could behave like they can perform clockwise rotation of plane polarized light, or they can perform counterclockwise rotation of plane polarized light. Now the question is, which sugar will be plus or which will be minus? If one isomer, do you remember we have D-glucose and we have L-glucose? Do you remember about this? When we studied about enantiomers? Okay. D-glucose is always plus. Means what? You will always find on your books, on your references, D-glucose along with a plus. Plus indicates that D-glucose, in which your OH group is towards right on carbon number 5. That glucose is always dextrorotatory. Okay. If it's dextrorotatory, that means it rotates light towards right. Now, is it possible that D-glucose will be then levorotatory? No. It's a mirror image. That means L-glucose will be always levorotatory. That means this isomer L-glucose will rotate light towards left. This is the best hint, best trick you have to understand. That in order to find or in order to understand which sugar is dextrorotatory, which is levorotatory, you need to remember out of two enantiomers, which one is dextro. If you know which one is dextro, then automatically its isomer is going to be what? Levo. Very good. So if D-glucose is dextro, then L-glucose is levo. Now what is going to decide whether D-glucose is dextro or rotate levo? You do not have any other rule for that. It's by default that this glucose is rotating plane polarized towards right, and this is rotating plane polarized towards left. And so you got to add something to your information. On your references, you will find always it's mentioned like this. D, then you have a slight space, then you have a bracket in which plus is written, and you have a glucose. So this is the representation, and you will find L like this. You will find L, a small dash, then you will find a bracket with minus. So you have information with this plus and minus. This plus and minus is giving you information about which isomerism? Optical isomerism. This is going to be, both of them are optically active, okay? Both of them rotate plane polarized light. But the thing is, this rotates plane polarized light towards right, and this rotates plane polarized light towards left. Even on some references, you will see this symbol for dextrorotatory. You will see a small d. So don't get confused anymore after my lecture. So you can see capital D, small d. Capital D is for enantiomers. Okay? Capital L is for enantiomer. But the small d or small l, they represent what? They represent your optical isomers. Small d for plus sugar, right bending one, and this one is minus sugar, which bends plane polarized light towards left. This is very important to understand in optical isomerism. Now let me take up the last type of isomerism which you will see here in monosaccharides. Let us take up the fourth type of isomers, which are EPIMERS. I hope now BL isomers, ANOMERS and your optical isomers are clear. Let us now understand EPIMERS. In order to understand them, I will be straight away going to the examples. That is the best way to understand, and that is the best way to get definitions also out of your knowledge, not by learning them and keeping them in memory and that making it difficult for you to judge the example later on. So I'll be taking simply like this. I'll be taking CHO. Simply I'm showing now aldehyde group like this. I'm not opening it into C double bond OH in order to save our time. So you will get these tricks now ahead. Okay. So you have finally this, and at that what do you have? CH2OH. Isn't it now easy to make? Then I will place H, OH, OH, H, H, OH, H, OH. My dear students, OH on carbon number 5 is towards right. Which glucose it is? D glucose. Let us add our knowledge of optical isomers into it. I will write down plus in the center. What does now it become? It gives you more information now. It means it's D glucose on the base of this OH, and now you have this plus indicating what? Optical isomerism, and it's indicating that this is a dextrorotatory isomer. Very good. Or you can represent this like D, small d, glucose. This is also a correct way. Okay. So we got to understand this much. Now, my students, I will draw another compound. Look at the board right now. I will draw another compound. I'll go like this. Then I'll go like this. This. I want to keep orientation same. That's why I'm. Then CH2OH. Observe this while I'm drawing. CHO. Okay. Observe. Now I'll keep all the groups like same. Okay. Except for carbon number 2. So here I'll keep OH, H. Here I'll keep H, OH. Here I'll keep H, OH. Around carbon number 2, I'll do something different. It was H on left side. I'll place OH. Then it was OH on right. I've shifted that. It's H here. Can you observe what has happened? There is a slight change between these compounds only at carbon number 2. Let me give you the name of this compound. This is actually, which is the pen? Okay, it's blue. This is actually D. This is another monosaccharide. I've given you lots of examples. This is D-mannose. Okay. How do D-mannose and D-glucose differ? Are they same? They're absolutely same. They only differ around, one carbon. So what is the difference point? Difference point is carbon number 2. They are differing at this. So out of 4 chiral carbons, you have 1, 2, 3, 4 chiral carbons. These 2 compounds are differing only at 1 chiral carbon. Okay, so they have difference at 1 chiral carbon. So there is difference in 1 chiral carbon. Carbon is actually same, but the difference lies in the arrangement of groups around this chiral carbon. If that is the case, 2 isomers are differing. They are absolutely same, but they differ in arrangement of groups around just 1 chiral center. Then you call these 2 isomers epimers. So what do I get to know? I get to know that D-mannose and D-glucose are what? They are C2 epimers. So D-mannose and D-glucose are C2 epimers. What does it mean? It gives you the definition of epimerism. It makes you understand what epimers are. They are isomers. Okay? They are isomers which are absolutely same, but in them difference lies in just 1 chiral carbon, and that chiral carbon differs in its arrangement of atoms. In one we have one arrangement around this chiral center, in another we have another arrangement of groups around this chiral center. Rest of the molecule is same. So if the difference lies in only 1 chiral carbon, then you will call them epimers of each other. And here, since the difference lies at which carbon? Carbon number 2. So we say D-mannose, D-glucose are epimers, but which type of epimers? C2 epimers. Now, still, if you have doubt, let me make one more compound. So CHO, then I'll go like this, then again, quickly. Okay, so you got so much of the practice. CH2OH. Let me give you numbering also, so that you will find it very easy. This is carbon number 1, 2, 3, 4, 5 and 6. This is the numbering I have given you. And this is also carbon number 1, 2, 3, 4, 5 and 6. So these 2 differ at carbon number 2. That's why I said they are C2 epimers. Okay. Same we will do here. Carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6. Okay. This compound which I am now making, this is actually the galactose I am trying. Now this will be same to this, okay, but they will differ at one place. Look at this carefully. H, OH, same. Then you have OH, H, same. Now this place will be shifted. You have H here, OH here, and in this case you have H here, OH here. So the difference lies at which place? 4. Okay, which is this compound I have drawn? This is D-galactose. What is it? D-galactose, which I have made. Okay, my dear students. So these 2 differ. Do they differ from each other? I mean to say, do D-glucose and D-galactose differ from each other? Yes, they differ. This is same. This is same. This is same, but this is not same. This is same and this is same. So they differ at which place? They differ at which chiral carbon? 1 chiral carbon or more than 1 chiral carbon? They differ at 1 chiral carbon. That chiral carbon is which carbon? Carbon number 4. So they are epimers because these 2 isomers differ from each other in case of their arrangement around 1 chiral carbon. So I will write down here D-glucose. So if you want to make definitions and all, whatever I am saying, you can write down that on notebook. That will become your definition. D-glucose and D-galactose. They are also epimers. From here you can derive yourself the definition. These 2 are epimers because, now the definition is like this, because they differ from each other. Epimers differ from each other in case of their arrangement of groups around only 1 chiral carbon. So it is same, they are same, but they differ from each other in case of their arrangement around carbon number 4. So I'll call them C4 epimers. What I will call them? C4 epimers. Now you can think about definition yourself. You can say epimers, suppose this or this, or this or this. Epimers are those isomers which are absolutely same. They just differ from each other in case of their arrangement at just one chiral carbon. They are called epimers. So I have given you examples over here. I have given example of mannose and glucose being C2 epimers, glucose and galactose being C4 epimers. Now sometimes after studying so much about monosaccharides, in competitive examinations, you are asked about modified monosaccharides, which are derived forms of monosaccharides. I would like to give you information for that also, because my videos are not meant for only board examinations, they are meant for your competitive examinations as well. So you must have this concept of derivatives of monosaccharides also. So I'll be just giving you overview. I'll not be drawing their structures because that could be complicated for you. In this class, inshallah, in higher classes you will see them, or in future if you will ask for their structures, I will be discussing that also. So let me give you an idea about derivatives of monosaccharides. Okay, it has started pouring outside, so I hope this sound is not going to disturb. So derivatives of monosaccharides are what? They are modified forms of monosaccharides. So if you have a general sugar, it can appear in biological systems in different forms. I'll be discussing their kind of modification, what sort of modification is there, which group is added to the monosaccharide, and I will give you one relevant example also. There are chances that in competitive examinations you will be asked about such things. So the first derivative of monosaccharides, I'll give you 4 derivatives of monosaccharides. The first derivative of monosaccharide are amino sugars. Okay, amino sugars. So you can indicate sugar, it's a monosaccharide, but they have got which group? Amino group. Okay, so in case of amino sugars, the new group which is added is either an amino group, or in certain cases you can have even a acetyl group, okay, attached to the sugar. Say for example, sugar is glucose, and at different places you will have either an amino group attached to it at some OH, or you will have some acetyl group attached to it. Now let me give you an example for amino sugars. The best example which you know from bacterial cell wall is N-acetyl glucose amine, which you call NAG. I hope you remember. That is a form of a monosaccharide, but that is not a simple monosaccharide. It's a derived monosaccharide. That's why we put these compounds under derivatives of monosaccharide. So you got to learn here that it is a monosaccharide which has got, even this has got both amino group as well as acetyl group. So this will be the best example to remember for which sugars? Amino sugars. Second category is the sugar alcohols. Now you can guess which is the group which is added to them is alcohol. Generally sugars have what? Either they have aldehyde group or they have ketonic group. If you will reduce this aldehyde and ketonic group to an alcohol, it will become what? It will become a polyhydroxy alcohol. Then that category is called sugar alcohol. So which is the new group in sugar alcohols? It is alcohol group. Okay, so in this sugar alcohol compound, you will not find aldehyde and ketonic group. That group is also converted into alcohol. Which is the example for this category is mannitol. Do you remember in EPIMERS I have shown you mannose, which has CHO. If you convert that CHO into CH2OH, that it will become mannitol. Okay. So third category is sugar acids. So now if you have aldehyde and ketone, you have that group. But other than that, you have one more functional group, NIV group. That NIV group which is now to be present is carboxylic acid group. Now if you have this group in a monosaccharide, already it is having aldehyde group. Suppose in case of glucose, it's having aldehyde group at carbon number 1. But now if the last CH2OH, 6th group, if that will get converted into COOH, that is the carboxylic group, in it then becomes sugar acid. So I will give you the same example which I was saying right now. Example is glucuronic acid. So glucose, if its 6th carbon CH2OH group is also converted into carboxylic acid, then it doesn't remain glucose, it becomes glucuronic acid, a sugar acid. Okay. The 4th type of derivative of monosaccharide are salic acids. Often you are asked questions about these. This is useful for chemistry also. Salic acids, you will find these compounds especially in fungal membranes. Okay. And this acid is having a new group. Which is the new group in this compound? The new group is suppose an acetyl group. Okay. The best example of a salic acid is N-acetyl muraminic acid. Don't get confused with N-acetyl muramic acid which you have seen in a bacterial cell wall. It's not that compound. It's a different compound. The name is N-acetyl muraminic acid. Okay. This is a salic acid which is not a normal monosaccharide. It is a unusual monosaccharide which is having acetyl group in it. It doesn't belong to this category because here you have normal sugars. But the sugar which is present in this case, the sugar, basic sugar here, is the muraminic acid, which is the basic sugar. So here you are not talking about glucose, lactose, you are talking about the sugar. Muraminic acid. It's a normal monosaccharide, okay? But if this muraminic acid gets modified, it gets an acetyl group, then it becomes what? Salic acid. Then that example of a salic acid is N-acetyl muraminic acid, which is present in fungal cell walls. So my job over here is to give you some derivatives of monosaccharides, which I have given successfully. You have 4 modified monosaccharides or derived monosaccharides: amino sugars, sugar alcohols, sugar acids, salic acids. Amino sugars have amino group and acetyl group. Sugar alcohols have alcohol groups. No more having any functional group. It's only having alcohols. Sugar acids have functional group. Basic functional group is present. But other than that, you have a carboxylic acid group. Salic acids are derived from muraminic acid, which is normal sugar. But that muraminic acid gets acetyl group attached to it and they become salic acid. Best example is N-acetyl muraminic acid. This was all I had for you people in today's lecture. I have kept the duration long because I get to upload just after 3 or 4 days because internet facility is not available. In Kashmir we have 2G internet and it takes me a lot of time to upload on YouTube. So that's why I'm keeping duration a bit longer so that whenever you get this video, you get ample information because you have very much little time left for your examinations due to COVID-19. So try to study today's video and understand it. I will be coming up with next video inshallah soon, and in that video we will try our best to cover oligosaccharides and disaccharides because I'm not giving you that overview information. I'm discussing in details. The same video is for 11th class student also. Same video will be used by a NEET student.
My dear students, it's pouring heavily now and alhamdulillah I'm done with my lecture for today. With this rain, I request you to just hit that subscribe button and press that bell icon so that you never miss an update from AmreenaMehrajTutorials. With these words, I wish you all good luck, stay safe, stay home, fi amanillah.